Now, the text of the exercise is the following. There is a drunk man, and this guy is at the 17th meter over a bridge, which is 100 meters long. So he is at point 17. Imagine that there are 100 points from 0 to 100. This guy is at point 17. The probability that he staggers forward or backward at each step is the same. So he has a probability 1/2 of going forward, and he has a probability 1/2 of going backward. Okay, so this guy is just drunk, so he's just moving randomly in one direction or the other. Okay, I want to know what is the probability that this guy will reach the end of the bridge, that is to say meter number 100, before crossing again the beginning. So I want to know if it starts going maybe 1 step, 2 steps forward, and then it goes backward, and then forward, backward, 3 steps forward, 2 steps backward, and so on. At a certain point, it should be able to exit the bridge from the beginning, so meter 0, or from the end, meter 100. I want to know what is the probability that it will escape the bridge from the end, so from meter 100. And I also want to know what is the expected number of steps that it has to perform in order to exit the bridge. In this situation, either from the beginning or from the end. Okay, so these are the 2 questions that I want to answer. Now, to solve this exercise, there are 2 possibilities. One possibility is to use Markov chains, as we did yesterday. You remember yesterday we played with the game of the coins, we played with the game of the 2 players, A and B, and we wrote down, so we essentially created the transition graph or the transition matrices, and we applied the different formulas, that is to say the absorption equations and the time to absorption equations. You remember the equation in the A's and the equations in the mu's. Now, this type of exercise can necessarily be solved in the same way, because what is just important for us to notice is that we have a state space that goes from 0 to 100. Each single I represents one of the meters, so meter 0, meter 1, 2, 3, 4, 5, 6, 17 is where the guy is at the moment, up to 100. And what we have, we can check what is the probability of jumping from one state to the other. And there are 2 absorbing states. The 2 absorbing states are 0 and 100, because these are the 2 states from which the guy can exit the bridge. Now, another way that we can use to solve this exercise is conversely by using martingales, and in particular by using the Walt equality that we considered yesterday. If you want to use Markov chains, what do we have? We have that the guy is here. This is state 17, okay? And then you will have state 18 up to 100. And the same here, you will have state 16, state 15, up to 0. Okay, so these are our states. And then what do I know? I know that if I reach 0, I stay in 0. If I reach 100, I stay in 100, because these are 2 absorbing situations for me. After that, if I'm here, I have a probability 1/2 of jumping plus 1. I have a probability 1/2 of jumping back, and the same for all the others. Okay, so it's always this. There is no possibility of staying exactly in the same point. And also here, obviously, I can have 1/2, and I can jump here 1/2. Okay, you understand what I mean. So if you want, you have this type of Markov chain, and you can apply the formulas that we have seen together. What you have to remember is that if you want to know what is the probability that you will reach this absorbing state here, essentially you have to set to 0 the probability of the other states that are absorbing. In our specific case is just this one. And if you are interested in the number of steps, in that situation, you have to check the situation that you exit from this side or from this side. So you have to sum the two possibilities. So if you use the Markov chains, I can tell you that the probability of escaping, so the probability we are looking for is 0.17, and the number of steps that you need, the expected number of steps that you need is equal to 1,411. Okay, so these are the two results. Now, what I want to discuss with you is how we can get exactly these results instead of using the equations that we have seen together, the absorbed bin equations and the expected steps equations. We can solve this exercise in a quicker way, so definitely faster, using martingales. So let's check that solution. At the end of the day, the result will necessarily be the same. Okay, so there is no discussion with that. Now, what happens? We have this guy, okay? So imagine that this is our drunk man. And this guy is where? Is at meter 17. Now, allow me to rescale the problem, okay? Such that meter 17 is where the guy is at this specific moment, and I call this state 0. Okay, so this is a new 0 for me. Now, from this state, this guy can move to state 18. It means that this is a +1. Or it can move to state 16, and this is a -1. When he is in 18, it can go up to 19, and this is a +1. Or it can go back to 17, and this is a -1. When he is in 16, it can go up to 17, and that will be, in this case, a +1. Or it can go to 15, that will be a -1. And every time it does that, given the assumptions of the problem, this is 1/2, this is 1/2, this is 1/2. So all these probabilities from one step to the other are 1/2, okay? Because it's a symmetric random walk. Now, if we use this representation, it is quite interesting because we can represent our drunk man walking on the bridge as a random walk, as a symmetric random walk that starts in 0 and can reach on one side 83 and on the other side -17. Why 83 and -17? Because obviously if the guy is in 17 and I rescale this to become 0, it means that 100 minus 17 is equal to 83. And 0 minus 17 is equal to -17, okay? So it's just a matter of rescaling. So what I want to check is what is the probability that this guy will escape from 83, so it will reach 83 before reaching -17, if every time his behavior can be represented as this symmetric random walk. So what I'm playing with is a symmetric random walk between -17 and 83 when I start in 0, okay? This is what I want to do. Now, this is a symmetric random walk, okay, that we can represent using Sn. So this is our symmetric random walk, Sn. What we have shown already, we have already proven that yesterday, Sn is a martingale, okay? And today we have just shown that the quantity Sn squared minus n is a martingale. Okay, this is what we have just shown a couple of slides ago. So these two processes are martingales. It means that if I take the expectation of Sn plus 1 given the value of Sn, this is Sn. If I take the expectation of Sn plus 1 squared minus n plus 1 given what I know up to time n, this is Sn squared minus n. Okay, so this is what I have just shown. Now, what I'm interested in is then the number of steps. This is the second question. The random number of steps the drunk man needs in order to escape the bridge. Okay? Now, this random number of steps can be seen as a stopping rule, as a stopping time, because we can assume that at every time instant, the guy makes just one step, okay? Forward or backward. So we can introduce a quantity n, which is our stopping time. And what we know from the result we introduced yesterday in order to give Wolf's equality was that if n is a stopping time and I take something that is already a martingale, Sn, the quantity S capital N is a martingale. And also Sn squared minus n is a martingale. So these two quantities, there is no need to prove that they are still martingales, because we are stopping two martingales with respect to a stopping time, okay? And this stopping time is a random variable that satisfies the condition that we gave yesterday. Now, let P83 be, so let P83 be the probability that our drunk man reaches 83. Okay, so it means that he escapes the bridge from the end, from meter 100, that after rescaling for us, it is 83. Let P of minus 17 be the probability that our guy reaches minus 17. Okay, so P83 is the probability that he reaches state 83. P17 is the probability that he reaches state minus 17. Okay? Now, by symmetry, what we have when we consider this situation is that the probability that the guy exits from state 0, that is to say state minus 17 after rescaling, is just 1 minus the probability of escaping from the other situation, that is to say 83. Okay, we are interested in the probability of escaping from one direction, that for us is 83. Necessarily, the guy at a certain point will escape from one side to the other. So the probability of escaping from one side is equal to 1 minus the probability of escaping from the other. Okay, so if we are interested in P83, P minus 17 is just 1 minus P 83. Okay, now let's use the following. What is then the expectation of Sn? Now, the expectation of Sn, that is to say the fact that at a random time n, this guy, our random walk will attain one of the two limit states, is equal to what? It is equal to the probability that I will reach state 83, which is P83, times the value of the state, which is 83, plus the probability that I will reach state minus 17, that I just showed is 1 minus 83. So if you want here, you can write P of minus 17, but we just showed that this is the case. And this multiplies what? The state minus 17. Now, this quantity is equal to the probability of 83 times 83 minus 1 minus P83 times 17. Okay, I'm just taking the minus here with this plus. Now, what I know is that S capital N is a martingale. So it means that if I condition this expectation with respect to the state I am now, it needs to be the same. So the expected value of S capital N, given that today I'm in state 0, given that at this very moment the drunk man is in state 0 because we rescaled 17 to be state 0, this is essentially the case. Okay, so I have that the expected value of Sn conditioned on the fact that my drunk man is in 0 now is essentially 0. It needs to be 0 because this is a martingale. And S0 is 0. So what happens? If I solve this, what do I get is that P83 is equal to, you see here I have P83 minus 17 plus 17 P83. So 83 plus 17 is 100, so it's 100 P83 equal to 17. So if you solve for that, the probability is 1.17. And P83, remember, is our probability of escaping from state 83. So we have just solved the first question. And how we did that? By exploiting the fact that our random walk is a martingale. You remember that we have said that something is a martingale if S, the value at time m, given that at time n I'm equal to a given value, it is equal to that value. Okay, so what we are doing here, what we are applying here, is the fact that the expectation of Sn, given that I start in S0 equal to 0, needs to be 0. Because it's a martingale. Okay, and this is true for every m larger than n. So if I choose n equal to 0 and n equal to capital N, this is what I get. Okay? Now, what happens in terms of the number of steps? Now, for the number of steps, I can use the second result. So I know that if I take the expectation of Sn squared minus n, this needs to be equal to what? It needs to be equal to S0 squared minus 0. Okay? Because if I consider at time 0, n is equal to 0, S0 squared remains there. But what I know is that S0 squared is equal to 0 itself. So at the end, I have that this expectation here needs to be equal to 0. Why is this result useful? Because now let's focus on this expectation. This expectation can be written like this. So it's the expectation of Sn squared minus the expectation of n, okay? Where n is a random quantity, okay? It's the random time at which I will exit from one of the two ends of the bridge. Now, this is equal to what? It needs to be equal to 0, okay? So it means that at any time, the expectation of capital N is equal to the expectation of Sn squared. Okay, so this is the expectation of Sn squared. So let's see what is the expectation of Sn squared. The expectation of Sn squared is the probability that at time n I am in state 83 times 83 squared. Remember that we are looking for the moment of order 2, so we have to square the payoff. So it's the probability of 83 times 83 squared plus 1 minus the probability of 83, 17 minus 17 squared, okay? But then the fact that it's minus 17 when I squared makes no particular difference. Now, what can I also do now is to substitute the value I know for P83, which I have just computed. The value that I got was 0.17. So this is equal to 0.1783 squared plus 1 minus 0.17 multiplying 17 squared. If you perform this computation, this number is 1411. And this is the answer of the second question that we gave here. So you can get the same result in two ways. You can use Markov chains, as we did yesterday, or you can exploit martingales. You see that if you learn how to exploit martingales and you remember that stopping a martingale at a random tile preserves the martingality. So if you have a martingale and you stop the martingale at a random time, this is still a martingale. If you remember this and you learn how to apply that, you see that here the number of calculations and the type of calculations that you have to perform is definitely simpler. Now, what I want to give you is also a general solution, okay? So imagine that instead of having state 83 and minus 17, okay? So you want to know what is the probability that your random walk starts from 0. So your drunk man starts from 0. And the random walk is between two limits. That is to say, a limit B and a limit A, where in our situation, B is equal, so let's say minus B, it's easy. So where in our case, it was minus 17 and this was 83. If you do like that, it means that A is equal to 83 and B is equal to 17 because you also have the minus here, okay? Now, the solution, the general solution for us, if you want, is the following. The probability that you will escape from A is equal to B divided A plus B. And in fact, in our situation, you see that this is true because B for us was 17 and we were divided by 100, which is 83. Plus 17, which is exactly 0.17. So if you remember this type of solution and you know how it comes out, it's just a generalization of what we have just considered, it helps you a lot. And if you are interested, conversely, in knowing the expected number of steps the drunk man will need to exit when the random walk is between minus b and a, this quantity is equal to a times b. And in fact, in our situation, if you take 83 times 17, this is 1411. Okay? So this is a possible way of solving the exercise. If you solved the exercise and you got these numbers by using the equations we saw the other day and using Markov chains, it is still okay, okay? I'm not saying that you have to solve necessarily the exercise using martingales. It's just to show you that, as usual, there are many ways in which you can solve the same exercise. And using martingales, you come out with a quite elegant and general solution that at the end of the day is this one. Okay, so if you have a problem, whatever type of problem, so now we are considering the drunk man moving, but if you have a problem that can be restated as a symmetric random walk, and you are able to rescale everything such that the starting point of your problem is now a 0, and you are asked to check what is the probability that you reach one of the two boundaries. If you are interested in knowing what is the expected number of trials, the expected number of time instants, the expected number of steps that you need in order to reach one of the two boundaries, and so on, then you have a general solution. So you can, I think that you can easily imagine that we can create an infinity of problems that can be restated in these terms. So this is a quite powerful result. Okay, so my suggestion is solve the exercise in this way. This is an extra exercise that makes sense to be checked. You already have the solution, so you can check immediately if your computations are correct, or at least hopefully my computations are correct. I hope so. The other way is to exploit martingales. And in exploiting this result, you are elegantly using the fact that a random walk is a martingale. The squared random walk rescaled by n is a martingale. And when n is a stopping time, everything keeps being a martingale. And the fact that it is a martingale is extremely useful because you can exploit this fact. So at any time point, even if I'm looking at very far away in the future, if I condition this expectation with respect to the initial state, then this is equal to the initial state that I have observed. And for me, the initial state is 0 because I've rescaled everything in order to be 0.